review of what we covered last time. All right, Sander, right? Sander, please remind us what the topic was last time that we started. Just name it. If you're not, for any reason, not comfortable to respond, simply say pass, and I don't. You said pass?
Yeah.
Okay. Johnson?
Who was Benji?
Benji. All right. Jack? Give us please the equation for radius of curvature. And Nathan, I assume you would pass, right? Because you did not get a chance to look at the lecture video.
Yeah. I
AJ, you please prepare for the equation for normal stress due to bending.
Can I pass for now and grab one?
Sure. You have that?
I'm gonna have to pass.
No worries. Audrey? Radius of curvature equation? So that's the issue with virtual class, right? You think everything is in video, you may not get a chance to write down things. You say, oh, I have it there, I will do that. So that's the issue with online attendance. Okay, anybody wants to respond? Yes, please.
Equation for radius of curvature.
Curvature.
Rho equals E times I over M.
Evan Mushner, correct. Rho equals EI over M. And then Leo, give me please the equation for normal stress due to bending. Guys, you're welcome to write this down in your equation sheet. Right? Something like this is show up in the test. J is for torsion, that's the Ethan? Don't have it. Gabe first. Robert?
What's the question?
You're not even in the class now. I said it one more time. Normal stress due to bending. Give me the equation for that.
Normal stress. Is it a
No, make a statement.
make a statement?
It is.
Sigma x plus or minus f over a plus or minus m z1. No.
Anybody else?
Is it,
It is.
okay, it is m times y over I? Or
Correct.
the absolute value?
Correct. You said plus minus, sigma equals plus minus, MC over I. So that we factor
MC.
accounted for either axis. Right? MC over I. M times C over I. If you say for Y, then it would be with respect to the particular axis.
Oh.
Okay? So that's how we would do that. So Braden the point, sigma, normal stress due to bending, it is plus minus MC over I. And speaking of that, we move on to Josiah. Josiah, if I bend this downward, this is too much to bend that. If I bend it downward, which face gets positive stress, which face gets negative, which face gets zero stress? For that, visualize the deformation. The face that elongates is positive. The face that shortens or wrinkles is negative. And the remaining one, let's see if we figure it out. Which one is positive if you bend it downward?
The side your right hand is holding.
On top.
Yes, on top.
Which I do have both. All right, top is positive.
And then the bottom side would be negative, and then the cross section would be the normal.
Very good, very good. So, yes, if you bend it downward, you see that this top or my hand stretches, the skin stretches, that's positive. The inside wrinkles is negative, and the mid face on the cross section, it is zero. I point to Josiah. And Cole, current stress is 0, what axis do we call it? Joseph was about to say that.
I'm gonna pass for now, my notes are kind of scattered
Yes.
because of the online lecture.
Got it, yes.
Or it could be the neutral axis.
Neutral axis. That was open question. That's an extra. I'll give you another opportunity. A point to Drew. Neutral axis is where you have no stress on the cross section, or no deformation, or no strain. All right. And then Drew, remind us so we said normal stress due to bending is MC/I, right? Give me the big name for I. The name for I. What's the name of I?
Not to be the second moment of area.
Very good. Second moment of area. All right, Wasi, what does it measure?
It measures the resistance to bending.
Very good, resistance to bending. All right, Nathan Smith. Thanks. Max, just to be fair to everybody, I put 8 minutes left for you, late for you.
Makes sense to me?
Okay.
Sure.
All right, thank you. All right, so Wasi responded, Nathan Smith. Let's see. Wasi and Kiro, the same question, different geometry. Give me please I for rectangular geometry, and you give me please for circular. I equation for rectangular geometry. I don't expect you to memorize it, just to look at your equation sheet if you have it, or the notes from last time. You have it? Last two examples we did, yes,
Yeah, is it, well,
it is.
hopefully, it is pi over 2 r to the 4th?
Was it J?
Or, well, I have j equals I y plus I z.
Then each one should be half of that. Then pi over,
Pi over 2.
no. If J is that, then I should be half of that. We did so many I calculations last time, right?
Yeah.
Do you have them on your notes at all?
I have iy equals 1/12 e to the third, or base to the third height.
That's for rectangular.
That's for rectangular.
The other one you said, that's half of that. Yes, Jacob, go for it.
Set the pi divided by 4.
4.
To the 4.
Half of pi over 2 becomes pi over 4. Yes, Jacob. And Kiro for the rectangular you said. But guys, we went over that. Instead of saying it that way for rectangular, say it this way, so that for different axes you have easy time. For rectangular geometries, I simply say that's 1/12 base times height, one of them cubed. Which one? The one that is perpendicular to the axis. This way, you're not married to the axis. If it's 3D, it's easy to figure out. All right, Jacob, your question now. Let's see what I have. Remind us, please, parallel axis theorem. When we do use it, what is it?
Wrote the equation back down here.
It's okay.
So I'll pass.
Just that. Your bonus operator question helped them. So parallel axis theorem, you said that will be used not only in this course, but also in fluid mechanics, also in machine design.
Let it pass.
All right, yes, John, was,
Would you like the formula?
just tell me something, let's see what you remember.
I have the formula written down. I have
Go for it.
I y equals I y plus p squared a.
The first one, I what? What was the subscript?
The subscript was y prime.
Y prime, yes. So it's basically this. If you know I about an axis that goes through the centroid, what is I about another axis with an offset from the first one? You add the I for the first one by d squared times area. D is not diameter, it's the offset. And that works for every geometry, not just rectangle or circle. All right, and then I go down to here. Okay, then, so we said there's something unique about I-beams. What do you remember? Why it's used in practice?
I don't remember what was unique about it.
I saw, yes, cool.
It was because it's basically the same strength and it's cheaper because you can remove the material.
It's much lighter, but almost the same strength. Not exactly the same, maybe 98%, but really lightweight. That's why people use that. All right. Right, again, I'm really giving you a prelude to the test. If you do not write these down, that's kind of what happened, the same thing that happened in test one. Really, there's no catch there. I'm just repeating things so that we all learn. All right, maybe one more thing, sturdy. When we calculate the stresses and then we graph the stresses on the cross section, we call that something. All right, Dylan, do you remember that?
I don't know if you do that.
Anybody remember that? Bossy?
Was it the stress profile?
Stress profile. All right, great, I quit 15 minutes late for you.
That's fair.
Thanks for understanding. All right, so we did that. And next will be you, let's just remember that. It's your turn. All right, we're going to do this example. And this setup is somewhat from the textbook with a lot of simplification. I'm giving you 3 different problems on the same setup, but with different descriptions or statements. And each one has its own mathematical needs. I want you to be familiar with these nuances. As engineers, it's really important to be prepared for those. And you'll appreciate the differences between being an engineer or simply a mathematician. Virtual, at least I'm not loud, right? Here I have to be loud so that everybody catches.
Bless you.
All right, for this leg, I would suggest this approach, and it should help solve the problems. So first pick coordinate system. And write down stress equation. In doing this, we have to be mindful, enumerate loads effects about centroid, so suppose that we switch to blue. Whatever coordinate system you pick, stay with it. The result will be correct in that coordinate system. It's given to you, so much the better. If not, pick one, stay with that. Make sure it is a right-hand system. That means, if you learned it in physics, if you put your 4 fingers of the right hand along X, you rotate them toward Y, the thumb of your right hand should point to Z. That's called right-handed. Otherwise, it would be left-handed. In engineering, we want that to be right-handed. All right, so I pick my coordinate system to be like this. I stay with that. It's labeled as M. It's from textbook again. It says it's curling around, in this case, about Y. So I name it as MY. Says point stresses and strains at different points. So divide the equations. So stress, we just learned. Let's review that. Nick, please remind us. Stress due to bending. Give me the equation, please.
Plus minus MC over I.
Very good. Let's switch to red. I'll leave some space because I that you said is recurring and we can calculate actually much easier. Jesus, remind us, this particular geometry, again, the textbook made it mathematically complicated by requiring us to do a lot of things. But this particular geometry, we did the I calculation for that. So if I put, this is the centroid, we calculated this, the very last example, last session. Do you have that value? Give me this length. And Braden, I want you to give me the I for the horizontal axis, the last problem that we did. So slide 6, then we know this height and the I value. In this case, I is about Y, but there we may have called it something else, a different axis. But the one that has horizontal axis, what did we call it, Braden?
What was the value?
What was, first of all, the label of the horizontal axis there?
Oh, it was IZ.
Z. In this case, it's Y, IY.
Yeah.
But give me IZ would be the equivalent to IY here. What's IY? I see that you found there.
8 times 10 to the negative 9.
8.68 times 10 to negative
Negative 9.
negative 7, in fact. Maybe you miswrite it. Miswrote it. This is what we did there. So actually, I have it here.
Oh. So looking at the second example.
Yes, it's just needed before.
Yeah, that's what I got.
All right, grade and a point. Jesus, do you have this height that you calculated from central calculation?
I see that we got I is
Why we
IY.
have it? Now give me this height that we calculated from that tabular approach.
It seems that we got 2.88
No,
times.
this height. Just look at your solution.
Oh.
Give me this height.
I have to pass.
Central calculation. Do you see that in your own?
I did not get that.
All right, that's fine. Let's revert. All right, open question.
Oh, I was gonna answer.
Over it.
38 millimeters.
38. Again, slide 6, we did this. So that you're not burdened with calculation of that, these two items. Let's have engineering discussions instead. All right, just the point. All right, let's reverse it. Braden, I go with you again for your second round. So I scored 4 points. So let's put this, and then, actually you tell me, what is the equation for strain?
For strain. On what?
Strain, give me the equation for strain, of what?
Oh, it's force over area.
That's stress.
So,
May have been part of the test. User is ready for it. Go for it.
I think tau over V over A.
That's shear stress. Here.
Strain.
Almost at the same time, give you each a chance. Yes, Kiro?
It is, I guess the backwards letter E equal to elongation over
Nathan?
Yeah, it's, epsilon equals, stress over one.
Not stress.
So it's the, I don't know exactly what it's like, it's probably
Delta.
delta.
Yeah, write it down, delta.
Delta?
Yes, so this is delta. I mean, it's Greek, it's not me, it's Greek. And this is C. All right? So Kiro and Nathan Smith. Yes, epsilon equals delta. That's the definition of it. However, there is a catch. First, let me give you guys a point. Nathan Smith and Kiro a point. All right, if we happen to have deformation and length, yes, we do that, and we calculate epsilon. So this is always true. But in elastic region, so open question, if you know stress, how would you calculate strain out of stress? You may have learned it in materials also. Anybody remembers that? If you know stress, there's a way in elastic region to find strain. Yes.
could you find the deformation and then just,
If you do that, then it would be this. Yes,
Hooke's law.
Hooke's law. We had sigma equals E epsilon. Hooke's law. It's valid only for elastic region. Then you can use this. Again, this is really the Hooke's law. The elastic region is a constraint on it. Remember that assumption. Here, another point. All right, so we use this equation, epsilon equals sigma over E. So once for A, and we said M is about Y, M and I get the same subscript, and C gets the point subscript, so CA. Repeat this. I think, Jesus, your turn, the one that you answered was open question. Jesus, what inspection, look at B and C. What can you say about stress? If you know the stress for this, what can you say about the stress of point C? And it's bending about this axis.
It's gonna concurve downwards.
Downward, correct? But if, suppose I tell you that the stress at point B is 10 megapascal.
Mm-hmm.
Does that tell you anything about point C?
It tells us that it's gonna have 10 times more force that way than point C. It's gonna bend more down.
So, okay, I got your answer. Nathan, what can you say? Nick, I'm sorry. If I tell you the stress for point B is 10 megapascal, what can you say about stress at C?
Which way is it bending on the?
Downward.
Outward? They can be the same.
The same.
Oh.
To the symmetry, right? They're the same distance away from the bending axis, so they are the same. So for that reason, really this is also sigma C, and our calculation will show also. So let's take this shortcut for now, and then we'll figure it out by equations also. So D decrease before I forget. Remember, M and I get the same subscript, and C gets the same subscript as the point of interest. So we develop our equations, then we plug in values. All right, then I want you to help me with picking the signs. So it's bending downward, right? So if I bend it downward, the top face, is it positive or negative?
Top face is positive.
The bottom face,
Negative.
mid face,
Neutral.
you said a 0, right?
Yeah.
So then, in this case, it's bending downward too. So you said all these will be positive, and all these behind you will be 0, and then you said this is neutral axis. Sigma equals 0. All right, and then point 2. All right, then pick the signs accordingly. All right, thirdly, we want to fill these up with numbers. M value, these from statement.
3 times 10 to the seven.
Kilo, right? We're all mostly multiples of 3.
3.
3. All right, so repeat it. And then the I value that we said we already found is,
It's 8.68 times 10 to the negative 7.
all right, let me have enough question for everybody. So move on, 30 point. All right, Aidan. So the C value, do you remember the definition of C, how we would calculate C value? Yeah, you're welcome to take a look at your notes. That's a for us. Guys, for this leg, it's all really this. Make sure you're able to calculate all these ingredients correctly based on the instructions that we went over. So maybe last example we did last class.
Ten to the negative third.
And what was the value you said?
10 to the negative third.
But see, really, see that we have, that's fine, I'll help you with that. And then you tell me, I remind you of the procedure, and then you tell me the value, okay? So we have C, A, C, B, C, the different values, right? They depend on point of the cross section. It cannot be just one single value, okay? So we said this is the bending axis. We said it's bending about Y, right? And Y, I drew that in here, in dashed. So once you figure that out, put these perpendicular arrows on that. All the time do that, once you figure out the bending axis. You measure C in that direction, from that bending axis to the point of interest. So then, what's the distance between that and point A? That will be your CA. Give me now CA, please.
It'd be 45.
So when we say CA, it means this, right? From this all the way to A, in this direction. You see that is this. Now figure that out. What is that? What is this? What's the value from A to B? 20. What's the value from B to this point? From bottom is 38.
2.
Then overall it is
22.
22. Milli is 10 to?
What?
Milli is 10 to?
Third. Or 6.
Look at that. In your equation sheet.
Negative third.
Negative third. All right, help me with CB, please. C sub B. Just 2. And give me CC, please.
Also just 2.
That's why we said sigma B and sigma C are the same. All right? Now, please give me the last one, CD.
38. Or
38. Guys, again, put this procedure or instruction in your equation sheet if you tend to forget things. I happen to forget a lot of things, so I simply write them down. It might help you as well. All right, 800 points. All right, we're going to calculate this. So sigma A is 76.04 megapascal. In your calculator, you should get an extra times 10%. Yes, Jake.
The C was positive.
C always is positive, it's length.
You went two directions, but
Yes.
either way, so.
Yes. The textbook said a different thing, I went over last time. The textbook says the sine of sigma is the product of sine of M and the sine of C. And it complicates it.
Yeah.
So that's why I combined them to one and I gave a geometrical sign to it, easy. All right, so that's that, and this one will be 6.91, and this will be negative 131.34 megapascal. All right, because this is straightforward, I want open question, so maybe several of you could raise your hand. Different names of the parameter E. One person, one name. 1, 2, 3, 4. All right, let's go for it.
Young's modulus.
Young's modulus. Josiah. Mossy.
Modulus of elasticity.
Modulus of elasticity. And then Hero,
I was just gonna say modulus, but, it's okay.
because you didn't know what you want to say, I trust you. There was one more, I believe, at least. Yes?
I was gonna say elastic modulus.
Elastic modulus. People, so one more hand, was it you?
I was gonna say last much.
I trust you as well. So Jacob and Justin. One is left. And you said actually in the test. Anybody remembers? Yes.
Second polar moment of area.
No, that's J.
But
Because you're AJ, that's J.
Yeah.
No, but I'm talking about E. Seven. Stiffness. Stiffness. So stiffness might be more political term for it. The other ones are more technical. If you talk to a builder and they say stiffness is this, that person most probably understands this one. All right, then we have the value, so sigma A. So open question first come, first served, what's G in giga? I'll just say it was first.
Modulus of rigidity.
The value. Yes, okay. 10 to 9. That's intensifier for Pascal. 10 to 9, Drew gets the point. All right, then we have everything. So here, the value I'm presenting it in mega, I can present it in giga, I can present it in Pascal, but in here in the equation, I should always convert it to SI, which is Pascal. So convert it to 10 to 6 for mega, and E is at 165, 10 to 9 for giga. So the value epsilon is unitless. Delta over L is unitless. And normally the value is really small because the formation already small, divided by big number because even smaller. So normally people convert it to an intensifier. If you convert it to micro, because it's dimensionless, micro by itself is pronounced as micron for epsilon. So this is 461. Open question, what is micro? What's the value micro? I saw again,
It was 10 to the negative 6.
10 to the negative 6. .91 times 10 to 6. .42 microns. So the more the stress, the more the strain, the more the deformation, and it makes sense. And what this is supposed to do, and do a suppose question. Remember that in this course, our goal is to be able to comment on mechanical safety of objects. We want to do that now. We have to know material property. Suppose sigma ut, strength in tension, is given as, let's say, 100 megapascal, and sigma u in compression, that is C, let's say it's 150 megapascal. Now, based on these calculations, we want to analyze whether the system is safe or not. But please remind me, who was the last person that responded for his turn. Hero, did you hear, have to read first. Help me guys. Aiden responded with, for C values. You were the last one. Hero, you then, yes, your turn then. All right. So Hero, based on these two values, would you say A is safe and why?
I would say it's safe because it's below both.
That's it. As easy as that. So in the test, you don't have to give me any more explanation. You say, this is greater than this is strength. This is the maximum value it should take safety. But you're giving A only 76. So this is below that, that's it, that's safe. So A is safe. All right. And Jacob, you tell me please about B, and then you tell me about D.
It's also safe because it's under 100.
That is it. So Jacob, Dozama, and Hiro.
D is safe.
What is your reasoning?
It's in compression. Because when it's negative, it's getting compressed.
Very good, very good. Because you're comparing this with what value now?
150 megahertz.
150. So just so that we have a different scenario, let's just simply switch to 130. Then it would be, if I change this to 130,
Oh, it would not be safe.
it would not be safe. So just to have a different scenario. So this is not, this is safe, you said, that's correct? And D, not safe. So, Justin, overall, is the same system safe or not?
Not safe.
One failure,
It's too many.
too many. All right, Justin, a point. Again, that's why we do all these calculations. Now, let me give you another insight. So in practice, it's really hard to calculate stress from a 3D object. Guys, please. So let's say the body of the airplane. You would not be able to calculate stress immediately. Instead, you calculate strain, you measure strain by strain gauges. So you use strain gauge. It's basically a combination of resistors, different architectures. You attach it, you glue that, is one way. You glue that to the surface, and it gives you a measure of strain in different directions. Once you have deformation or strain, once you have this, then you have deflection. Or once you have epsilon, then you have this, you have sigma. You do actually the opposite in practice. So this is, this attachment of strain gauge is a non-destructive attachment to the object. All right, one example of this setup, as I promised, there are two more in the same setup, but different statements. Before that, any questions for me, guys, on this problem? All right, let's move on to the next one. We got the same setup. So Justin, I'm sorry, Nathan, be prepared for it. Still, we have the same values from slide 6. So let's go with the same I, we said X, Y, Z. Before this, let me give you another insight to this. Guys, we calculated the stress for point A. For what direction do you think it is? We have 3 axes. We calculate the stress value, MC over I, but what is the direction of stress? Yes, Brent?
Is it the Z direction?
The Z direction. One opinion. I see why you say Z. Any other opinion? Yes.
Maybe the X because it's, I don't know, X.
You say yes.
Yeah.
But you had something, you had a reasoning. Just say it. Point
So if it's stress at A, point A lies on the top surface, which is in tension, which would be
You said
tension
it.
on
You
the
said it.
x-axis.
You said that. You said you gave me the reason.
Yay.
Yeah, cool. So the thing is this, no matter how you calculate it, we started with saying whether it's tension or compression. You said it. So it's moving, it's elongating or shortening in the x direction in this case. So the stress is really in x. So really, all of this is in x. So visualize the deformation, exaggerate it, and you will determine that orientation. All right, and then we said I about y here was 8.68 times 10 to the negative 7 meters to the fourth. So from sky 6. So you have these at our disposal. The statement types that one would be able to give you in this course would be really limited. One of them is this: what's the largest load that the system can take? Or what's the minimum dimension that the system should have to safely take the load? These are the same thing. Reagan, you remember the answer to that, right? How you solve for that. If I ask you what's the minimum dimension, what would you do? Forget about factor of safety. Suppose it's 1. What would you do? Remember? It's okay. It was just open question. Remember, I asked you this and you responded to that. Was he?
The failure amount divided by the actual place force.
Yes. Okay.
Isn't it ultimate versus applied?
You said
Ultimate over applied.
exactly. Exactly. So you push the material to its limit. So where it says find us or minimum dimension, the same concept. Gauge risk gets the point before I forget. So you push material to its limit, strength limit. So in this case, we're talking about stress, sigma u equated with sigma max. Had we had factor of safety, divide this by factor of safety. We did this in homework, we did this in review, test review, we did this also in the test. Now, whether it's leg 1, leg 2, or leg 3, the equation for sigma max changes. Because we're talking about different stress types. In legs 1, 2, 3, in leg 1, in chapters 1 through 3, sigma max is called F over area. That will do the equation. In this leg, it's mostly MC over I, depending on the loading type. So really that's the only difference. Otherwise, this is the criterion that we have to use. Reagan, you remember this now? All right, this is what we're gonna do. Guys, please remind me, this was Nathan, right? It was your turn?
Yeah.
Okay. Nathan, when we do this for the weakest point or position in the material. So look at this example. Whichever point gets the maximum stress, magnitude-wise, that is the critical location. So which point gets the maximum stress based on our analysis? sorry, I can't hear, say loud.
Would it be decent?
Make it statement. Make it statement, it is D. Not asking. So there are two things. If you look at the compression, it would be D. But if you look at tension, A. All right. It's either A or D. So let's go back in here. I get back to you. Anybody knows this? What sigma Y refers to? Professor Kurmova may have gone over that. Yes, yeah.
Is it a yield strength?
Yield, yes, yield. So if I do this sigma versus epsilon diagram, before I forget, Leo gets the point. So we said in this region, which is elastic, and this region is plastic, we said yield is here. Basically, the cutoff point or the boundary point. And sigma U is in here, ultimate. We said in this course, the two are equivalent because this is an introductory course. We want to be easily able to write down the equation for this line, which we said is Hooke's law. Sigma equals E epsilon. So in this course, if you see sigma Y, it's the same as sigma U basically. All right. Now another question. So we want to again make that decision as an engineer, whether I should go for the point A, which is basically top point, top face, or bottom, which is basically D. Make that decision, then I have to figure out what kind of material it is. So sigma Y is given to you. What do you think? What material is it? Anybody remembers that? So I'm doing my best to ask you conceptual questions rather than mathematical, yes?
Is it like a type of material?
Yes.
Is it a ductile material?
Is it ductile or brittle? Your answer is?
It is ductile.
Ductile. What is your reasoning?
A brittle material would go up and then it just break, while a ductile material would kind of deform a little bit.
I understand. This curve that I gave you was not for this case. I'm just asking for this value, what would be your decision? But because you named it correctly, I'll give you a point. I asked other people for everybody then for why it is ductile. Just that point. Again, as an engineer, you go to Home Depot, you want to pick up a material, right? But looking at that number, you should be able to deduce that. So we said in ductile materials behave the same way in tension and compression, right? If one value given to you, that means they're the same, right? For that reason, you would say it's ductile. Then Nathan, ductile material. That means one value is given to you. That means if I were to redraw this or extend this to negative sigma and epsilon values, it would be something like this, basically the same thing, symmetric. So sigma Y would be the same for positive or negative. Then would you say point A is more critical or point D based on these values? The capped value that it can take is the same for the two. Which one is more critical? You had said it early on. Repeat it.
D.
D. Because it gets more stress, right? You do not care about the sign then because in either direction it's the same thing. Then, yes, because it's ductile, then D is most critical among all of the points. So really we have to do this for point D. In this case it's 1. So Nathan Smith, a point. So we said it's 300, go up to Josiah, what's mega?
10 to the 6th.
Very good. And then remind me the equation for normal stress due to bending.
Normal stress due to bending is MC over I.
Very good, and we did see that's about Y, it's repeated from the previous problem. And we said CD, the bot, or let me actually, yes, CD. Point to Josiah. All right, and while we are solving for it, leave it as unknown. Code, remind me the CD value. This is the bending axis, y-axis, go always in this up or down perpendicular direction.
Okay.
What's CD?
So it would be 38, right?
38. Midi is
Times 10 to the negative third.
very good. IY per our previous calculation is
8.68 times 10 to the negative 7.
all right. We have this, guys. In your test, I'm going to return it to you shortly today. To calculate something like this, some of you did several steps, but you learned how to do this quickly. Cross multiplication. Again, as a review, put 1 in here. You want to solve for this? Draw the fraction line, put numbers on top and bottom. On top, go the numbers that are off diagonal to my. As here, off diagonal are these numbers. These are on the same diagonal. So these numbers go on top, cross multiplication. Really, you don't have to do several steps. Whether remain on the same diagonal, put them in the denominator. That's it. So if you calculate this, and if you convert it to kilo, you get this. So that's the max that they can take. And if you give more, call the point to you. Drew, if I give more than this value, more than this, what happens?
The material will start to be damaged and will eventually break over.
Very good. At which point?
At point, at point B.
Yes, at this point that we find to be most critical. All right, if you want that to be safe with a factor of safety of more than 1, then we have to strengthen that point or lower the max load that we're applying. All right, give you a few more minutes. Any questions, guys? Bossy?
Yeah, everything except for, how do we know who's ductile?
When the material property that is given to you, it gives you one value, that means it's the same in either direction. Unless it's specific, it says different values. Not mentioned, it's ductile, it's just one value. Yes?
So for the example we just did for this one,
Yes.
for when we did the safety factor, that would be a brittle material?
No, factor of safety is something that you,
For the 2 stresses that you gave for the last part of it? Because you gave 100 megapascals and then 130.
oh, I see. Those are, no, yes, that's for brittle, because the 2 are different.
Okay,
Yes.
all right, thank you.
Because as soon as you see 2 values, it's not ductile for sure. All right, so guys, I suggest we take the 10 minutes break now. Please come back by 11:26, and then we do this. And then you're welcome to take your test from here. It's in alphabetic order. Please do not mess it up.
You look ready. Give me a second. Sleep center. You give your side. I just saw my own. I forgot.
Yeah. I put
I'm getting over it. Right?
Jeez.
Just a lot of drainage. It sucks. It's just gross. Yeah.
When you're afraid of
When you're afraid of it.
so.
You just can't let it know. I like that.
What's your family that starts with?
That's really.
wrong there, but that's what
I'm not even gonna.
Yo.
The true false one is still in. Yeah, it was. Yeah, it was. I got the true false wrong, and then 24 off.
I got.
False true.
Yeah.
I'll take it.
I'm not complaining. Honestly, so, yeah, I have it by first or last time. But I used the wrong number.
Did you use one of the ones that wasn't correct?
Yeah, I used, stress, yeah. No, shear. Shear stress? I used shear.
I used,
I did. 24 out of 40, 20 out of 60.
I really messed
I
up.
don't know. Let's see. I got. Yeah, so, I thought about this, I had it as false, and I was like,
confused. Oh, tension.
what's that?
Wow.
I felt,
That's tricky.
I can't remember.
I didn't see the tension.
I have to change this, I have to change this. I didn't change it for some reason.
Well, here's the thing, here's the thing. I automatically just saw 30 to 45.
If you it's just like, but you see this,
it's kind of crooked, I can see
you could be.
No, that's true.
Like you see, I think.
If I just got, like, it's right. 100%. That's so sad.
Yeah.
I don't know what to do.
I'm feeling like shocked, like, how you snap it.
Yeah,
Yeah, I don't know why, that's what popped in my head.
Ethan Jackson, right?
Yes, sir.
I wrote down, so that are
I think it depends on which section. So F2, I mean, of course, there is an class, when you say F2, just say that there is both here, F1 starts just this, go toward that. So F2 is both in here, this is just pushing, right? Negative, F1 is pushing. So the force here is negative, and the force here is F1.
I was just curious.
But you got it.
Yeah, I was.
Exactly. Isn't this something we did here? That should be
Yeah, it was just the fact that one was expression, one was.
600
That's the part here.
So these are,
So that's where I thought that maybe. That's a little, that's, I just wanted to know the reason of why.
So, 600 minus 400 is 200. It says this is more, it's pushing in.
That's not very my impression. I misheard the question.
So this is 5. I mean, DNC's, sorry, and, so this is not bad. This makes sense, this force is still one chunk, so the first one still needs a So, what is the force one still? Is that what we talk about? Never taking it, then always consider that. Unless they say that they can get taken advantage, which would make no sense. Not occasionally. Yes, so this force, if you think about it like, if you think about it, let's say, where's my pencil? Here, yeah. Let's say this pencil is securely fastened in this column. Me pushing on the tip of this pencil is still putting the same amount of force I'm putting on this pencil on this guy. Does that make sense? There is no force loss between them.
Next question.
So if I'm pushing on it like this, the force I'm applying to this pencil is probably 1.5 is that's kind of like 1 magnet force from this thing. This is like straight force into the calculator. However, there's no force loss from if this was to create acid, then I pulled up, it would be the exact same thing. There's a pulling up that force equally. So, if you have, again, 200 kilograms of pressure, there's two more of that. Yeah, I mean, then you go, okay, it's compressed on now, so I'm gonna take the, strength. You do get a lot of points for strength and pressure. And it's just 1.6. So, next year, you can divide that by 2, and you get, we shall say 8 and then you put that, and then use the stress force from stress.
All right, guys, let's quickly go over test 1. So problem 1. So let's take a look at true false. Second polar moment of area does give a measure of resistance to torsion. That is correct. The grade of material fading due to tension, we know that abruptly fades. It's a clean cut. Therefore, it is false. That 45-degree cut happens when it's in torsion. What is the equation for deflection or deformation due to change in temperature? Delta sub T equals alpha L delta T, not anything else. Some of you put alpha E delta T. What is the equation for strain? We went over that also today. Epsilon equals delta over L. If you put epsilon equals delta over E, that would not be the equation for that. That is valid for elastic region. What is the equation for normal stress due to an axial force? The very first equation we learned, sigma equals force over area. All right, let's switch to the numerical problem. We did a similar concept I did myself, we did in homework, maybe 4 problem, and we also did several of those in the test review problem. The first, I think, multiple choice problem, you already did it all. Did for both segments there. For both, we just whether the first segment or the second segment. In this case, it's just segment AB. what's the minimum diameter? We also did it today. Sigma U equals sigma max. But sigma U should be divided by factor of safety, which is 2. Sigma max, the equation for normal stress is force over area. Area of the segment is pi for d squared. We are solving for diameter. The force acting on AB, it is F1 minus F2. I think we reviewed this, or again in test review, if you have F2 here, F1 here, even if we have more pieces involved, let's say F3 here. You said the shortcut is this. Once you see if this is clamped here, if F2 applies here, go to the other side, put F2 for every segment. This is pushing, so put negative F2 applies here, negative F2 applies here, negative F2 applies here. Paul, over here you were correct. This force applies all the way through. F1, if it's applied here, it applies every point past F1. So F1, because it's pulling, then put F1 in positive form for these two segments. And for F3, it applies only to that segment. So, and it's pulling, put plus F3 only for that segment. What's the force in here? What's the force in that segment? It is minus F2. What's the in that segment? Plus F1 minus F2, add them. What is here? Summation of all D3. So for AB then, in the test was F1 minus F2. Otherwise, it was really plug and chalk. Some of you, unfortunately, use the deformation equation. It's not applicable. Some of you use shear stress equation. It's not applicable. If you have force, applied force is axially applied. It's all about force over area, and that's normal stress. No shear stress. Even though you worked out your solution with the wrong formula, I looked at your work and tried to give you some credit depending on the parameters that you calculated. If you have any questions about the test, please come, about grading, come to me after the test. I'll go over that. But I'm just really surprised the average was low, but we had several complete scores. So well done to those people. But what happened really? Because it was a really similar topic we did in homework, majority of you got 100. So that's concerning me now. You got almost all of you got 100. How come you were not able to solve that in the test? And we also had these reviewed in the test review. You want to comment or not?
Yeah, I mean, I looked over, there was a test review on it, like, in the blackboard, and they had nothing to do with the test that was provided.
Are you saying that that was not the same as
I
this?
didn't see a ton of similarities between the test review and.
You don't remember this shape being given for the first four? This figure.
No.
Yeah, please take a look at that again. For the first multiple choice problems, I said what's the stress in this segment, what's the stress in that
No,
segment?
I'm talking about the test review that was given by.
No, the one that I gave, I'm
Oh,
saying.
yes.
The one before the test is on Blackboard. If you did it, if you submitted anything there, then you're able to look at your grades because your layout will be different from mine. But I saw from other students, if you look at your submission, your grades, then you're able to see all of that. Yes, Dave?
Yeah, I couldn't get it back open after we did it in class.
Yeah, it's not there, but if you look at grades, I just said, if you look at your grades, it's there.
Yeah.
You should be able to see it. All right, so any other opinion? 3 instances of the same problem, but I'm really surprised. Only several of you had 100. Many of you actually, maybe within 10 minutes, we finished. So I'm aware that we had, there are some difficulties at Kettering. One of them is the fast pace. It takes so many courses, and then it happens a lot that some of you get back-to-back tests on the same day because you have to give you midterm grades, early grades. So I understand that. It happens. But this is the first time that the average was this low, given all the review that we did. The type of review that I did for you this time was the first time I did. I gave you 14 to 15 problems. And I gave you all different problem types that could occur. If you really reviewed it carefully, it should have been pretty much more than 60 or 70 hours that you got. So that said, I care about your success. I would not think that if people got complete scores, I would be able to give you another chance. I never did it. But now I want to leave it to those people who got complete scores. Is it okay to you and give the other people a chance for a redo for certain points? Is it okay? Yes? All right, too? All right, thank you. Because of because of your opinion, now it's fair to give those people chances. So I'll post just a numerical portion on Blackboard, and then sometime today or tomorrow, it will be due on Sunday at midnight. I'll give you 2 attempts. It will be either 0 or however many points I give you there, and it will be added directly to your test 1 score. I will not do that again, because the grade should mean something, right? It should really be in line with your performance in class. But given the situation, I'm helping you this time. So please do that on time. You have 2 attempts for however many points I give there, and it will be back to your test 1 score. So that's from my end. But from this point on, going forward, seek my help if you need help. Perhaps this is one of the few times that I do not get people in my office hours much. Normally it's really populated. Take advantage of that one. If you need help, take advantage of it. It's free, right? It's free. Take advantage of it. All right, if you have any questions about grading, please come to me after the class, I'll help you with that. If not, then let's please finish this one. As before, this is the same setup, but this time the only change is that the material is brittle, because 2 material properties, one for tension, one for compression, are given. All right, so we said the same procedure. We set sigma u equal to sigma max. Once for tension, we found that the upper piece is in tension, so then we put top. And once the same equation, the factor of safety is 1, that's why I do not include it there. In compression, we put a sigma max for the bottom. Each one is capping the strength in the respective direction. So we should have 2 constraints. And because it's all about bending X, Y, Z, 38 millimeters, and I, Y, (868) times 10 to the -7 meters to the 4th. MC over I, and we said it's all about y-axis. This is for C top. Repeated for C bottom. And that's I1. All right, guys, please help me. Who was the last person? Justin, you responded, right? Nathan? So this was the last one.
It might have been me.
It's your turn, or you did it?
I think I was the last person.
Okay, thank you. And Drew, it's your turn now. All right, Drew. Sigma U in tension, please give me the value from statement.
Intention, that would be 28 times 10 to the 6.
Very good. All right, give me also the same in compression.
In compression, it would be 60 times 10 to the 6.
Very good. Again, when we say in compression, all is really in absolute value, it's positive. We're just comparing the magnitudes. All right, true point. All right, WASI, MY, we're solving for it, leave it as unknown. C top, please give me C top. You said, this is the axis, go in these directions. C top,
Sorry, what did you just say?
this is the axis, right?
Yeah.
I mean, you have to tell. You have to tell. This is the third time you're doing that today. The C value, look at the previous one, how you calculated that?
Is it 2?
C top. You're looking at any point on the top surface and the bending axis. Should be. Look at this, what did we do for this? It was C bottom, right? The bottom face. What was the C value that we used? What did you do? This is the bending axis. This is the face. So that's 38. Do the same thing.
22?
22. Midi,
10 negative.
negative third. And then all value,
And what was
I value.
it? 8.68 multiplied times negative 7.
And then in parallel, have you also with C bottom,
That'd be 38 multiplied times negative
yes. All right, this one gives us one MY value, this is another one. All right, in kilonewton meter will be 1.1 kilonewton meter, and this is about 1.4 kilonewton meter. So what's the point? And then I'll give you time to complete your writing, and then we want to have the final result based on these two values.
Can you repeat?
I'll give you time.
What was the last word?
I'll give you time. Finish that, and I'll ask the question again. All right, and then the top one, when you apply the top one, which face is about to fail?
Top surface.
And you apply the bottom one,
Sorry?
and then you apply the bottom one.
The bottom moment.
If you apply the bottom moment, which one will fail? Will fail?
Also the top surface.
But see, it came from which criteria?
The bottom.
It means it is
Bottom
fail.
face.
All right. So if you apply this, you said the top face is at the verge of failure. If you apply this one, the bottom face is at the verge of failure. Which one is the critical condition now?
The top surface failure.
Yes. So even though we are after the largest value, the max value, but we have to pick the smaller of the two. Isn't that refutation? It is, right? So it's a paradox. I put that exclamation for that reason. You have to pick the smaller of the two. So this is the final value that we have to write down. Yes.
You choose the smaller value because if it's below 1.4 in compression but above the 1.1, one fails but the other doesn't.
So let's answer. Let's think this way. If the load is zero, would the two faces be safe?
Yeah.
Increase it, increase it, increase it. As you increase, which one gets to fail first?
Go up to one.
Then that should be the one.
Okay.
You do not even get to the second one.
So even if one fails,
That's too much, too many. So that's the difference between, again, look at that, ductile versus brittle material. Too much work on this one, twice the work. So be mindful of it. Just one subtle change, mathematical procedure changes, but all logical. All right, guys, any questions for me? Thank you for the confirmation. So we want to switch to a new topic. Actually, we want to generalize what we did so far. Guys, phone aside, please. All right, let's get back to theory slide. One item is left, and the textbook calls it combined loading. That's this. In practice, it's rare that you have particular force applied. You may have combination of those. Even when the force is applied, it's rare that it's truly axial. It might be with some offset that affects the system significantly. So how would we account for that? All right, I think it's easy. I would use the word modular, makes it easy. So if the load has any axial effect, you would say stress would be F over area. If any portion of the load has bending effect, you say it has MC over I effect. If it has both of them, you combine them. You add them or subtract them. You know that pulling is positive, pushing is negative. And we found about bending too. If downward like this, top face is positive, bottom face is negative. We know about signs too. So you superpose them. So if you apply just the force, you pull on it, F or area applies. If you're pulling, pick positive, if you're pushing, put negative. Now, if you apply the moment alone, we learn this, NC over I, put NC over I, for any of the axes that you have bending about. The text goes for Y and Z, all right, well, we simply do MC over I for Y, MC over I for Z. So we discretize the dimension into 2D, and then each one, whether F over A or MC over I would apply. That's really the logic behind it. We want to now showcase these equations, the combination of these, with different examples. I see some of you are writing, I'll give you a little bit more time. So that's why I call it modular. We have to know axial effect, that is sigma equals force over area. We have to know bending effect, sigma equals MC over I. If torsion applies, how would you do that? It's something harder to deal with. Then we have to wait until chapter 7, 8, and 9 in leg 3. All right, so let's do our first example on combined loading. So Tyler, it's yours, I'll give you time. Guys, let me emphasize, engineering is different from high school work or even mathematical work. We know certain equations for different modules, let's say, and then you have to combine them. And that requires analysis. That makes it engineering, whether that equation applies there or not. Better engineers are better at it. All right, as before, pick a coordinate system. All right, equation for stress. Enumerate load effects about different axes. In particular, for bending, about the centroid. So this big coordinate axis. So if I take this as x, as y, and z will be basically this. This is the cross section viewed from this direction. So this should be yz. That's basically normal to the plane of your paper or your tablet at point C. So whatever you pick, stay with that. You want to write down the equation. It does say normal stress, so it says minimum and maximum. All right, let's analyze it first. Have your calculators ready. The two calculations, eventually I want you to calculate and show me so that I give you bonus points. All right, so this part, please pay attention because you need this analysis skill. I'll give you time, once you pick that up, I want you to help me with this one. Are you ready? Are you ready? All right, so, I'm sorry?
Can you repeat what you said?
Yeah, I'm gonna do that now. So, we want to do now, the first part is done. We picked the coordinate system, right? All right, now we want to write the equation for stress. Sigma equals something. Remember, modules, axial effects, the normal stress will be, you remind me, normal stress due to axial force. What is that? Force over area. Force over area. For bending, look at the previous example. MC over I. All right. So it will be a max combination of these. You got that? Now we want to determine which one should be there, which should not be there, okay? So, by pulling on A, are you pulling on the system or not?
Yes.
Yes. Again, remember, if I put whether one force on the left, equal opposite on the two ends is the same as fixing it and hiding it. One is reaction. The textbook does it this way. All right, fixing it is the same thing. If I pull on F, is C also being pulled or not? Of course, if you stand there, you feel that.
Yeah.
All right. If pulling is there, give it a stress for pulling. We just did it.
Axial.
Yes. please write it down. It's absolutely fine to forget it. Write it down so you do not forget it. So that's normal stress due to axial force. So you said it's pulling, right? Is it positive or negative? And direction doesn't matter. I can look at this left side, then it's to the left. The effect matters. Are you pulling or are you pushing? Pulling, is pulling positive or negative? Positive. Then put plus F over A that you said. Let's now move on to the next module, bending. Had we not had this offset D, would you agree that it would have been simply pulling effect? It would be simply stretches, right? If there is that bending, would you agree that there is bending there?
Is there bending there?
Would you think there is bending there or not?
Yes, it would be.
Yes. Which axis do you think the bending is about? Remember, C is the one perpendicular to the plane of the surface.
Is the axis.
Very good. So how do you determine that? Well done. How do you determine that? Guys, do this simply. So it was like this. If I pull, I see that it flattens, right? It was like this. Exaggerate the deformation, and then it's curving around the Z that you set. That curve axis gives us the bending axis. So exaggerate the deformation, and then see it curves around which axis. That axis is our bending axis, as Tyler said. So Tyler, you said there's bending, you said it's about Z, but give me the stress equation for bending.
Would be MYC over IY.
You said, please say MC over I from this point on. But you said about which axis?
Z axis.
Z. Then you put subscript for M and I. So put plus minus because we do not know which point on the axis we're going after. So MC over I, so put Z for M and I. All right. Do you think, Tyler, is bending about any other axis? Does it deform in about any other axis? No, then that's it, we developed the equation. That's why I call it modular form. All right, Tyler, point. So, depending on, we looked at the previous examples, when there is only moment, top or bottom are either tension or compression. Mid-phase, we know that's 0. All right, then that's why I asked for maximum and or minimum normal stresses. So let's do once for the top. F over A remains the same. For the top, it goes to Olivia. Would you think, just visualize this, this opens up like this. So it's bending downward, like this. Would you think the top phase shrinks or wrinkles or stretches? What happens? That is a negative or positive? Negative. That's it. The negative, like that. A C top. And then bottom would be positive. Again, it really needs your engineering visualization and analysis. Believe in yourself. It's like driving. You believe in yourself. When you know how to drive, no matter where you go, even to new city, you're still able to drive. You always make that decision. Should I speed up? Should I slow down? Should I make right? Should I make left? You believe in yourself. The same in engineering. All right, we have these. Equation developed. By inspection, we see that the bottom one, both of them are positive, then this has to be max, this has to be min, because the two are subtracted. So Olivia, before I forget, point to you. All right, Reagan, you want to fill this up. F over A goes to you, and then the next term goes to K. So, Reagan, if I pull with the F at point B, what's the force at C? Any difference? So what's the value? Yeah, the value. 10 times 10 to? Third. Area is the area of the cross section is given to you. Give me the area, please. You don't have to give me the final value, just to say this times that. Centi is? Very good. All right, this portion is repeated because F over A is repeated. I just put this quote. We want to continue in here, actually specify can continue on the same line that we move this to the left. This is negative, this is plus, whatever is up there will be the same thing. So let's calculate only one of them. The point to Reagan. All right, get, yes, Nathan.
Are you able to zoom in to?
On the length?
Fraction you have for, stress. I can't
Which part?
You have 10 times 10 divided over 2. Is that 0 times?
This one?
0.8.
This, yeah, this, you see the length?
Yeah.
0.8, cent is 10 to negative 2. Yeah, but that's the cross section. All right, Gabe, so you see here, the focus, so it's really important that you're mindful of this thing. For bending, we calculate everything about the centroid. The centroid is here, which is point C.
Yes.
Look at the force F. What is the moment that it creates about point C? In statics, moment equals
One is the rotation.
something times something.
Oh, yes.
What is that? Force times?
Force times here. Force times something.
Moment. Olivia.
Force times the distance for the moment.
No, yes.
Tip of my thumb.
Olivia gets the point. All right, force times distance. Now give me that. What's the moment of the force? If I can see force, we said Reagan said 10 kilo, so that's the force. Give me the distance.
The distance would be 5 centimeters.
Centi is.
10 to the negative.
All right. Now, give me I. And we did so many I calculations. It's rectangle, it's about Z. So how would you do that?
Would it just be 0.8 to the negative 2 times 1.2 times 10 to the negative 2?
You had a coefficient too, remember?
What?
I for rectangle geometry. Review your examples, but how did we do that? We're teaching another course, and the student responds to me and goes, "What?" You almost reminded me of that person.
Yeah. IZ is 1 divided by.
So, okay. This is for the 10th time, please, it's for your sake. The z-axis there is defined in a certain fashion, right?
Yeah.
If we stick to that, then we should always know which one we picked. So let's not stick to that axis. We said instead do 1/12 base times height, no particular order.
Yeah.
Raise one of them to the third order.
Yeah.
The one that is perpendicular
Oh.
to the bending axis. Okay, it was on the tip of your tongue. I may have seen it from here.
Yeah. Yeah.
I'm joking. So again, 1/12, say it.
So it's 112 base temp height, and then height would be.
One of them cubed. Which one? Not height.
Base.
One of them. Which one? The one that is
Base.
to the bending axis. It happens to be height sometimes, sometimes not. All right? So you said 112. Base and height, you already gave me those, that's correct. The same values that are here. Which one should be cubed now? The one that's perpendicular. It's about Z, right?
Yeah.
It's perpendicular to Z. Which one?
The y-axis.
Very good. Give me the value. Which one?
Point. 1, 2.
1.2. Cube that one. So that's all. All right. Now please calculate these and give me these in gigapascal. Once you're here, make sure you give me both. So I give you 2 points. Do not come here, please, just for one of them. Do both. So take advantage of storage capability of your calculator. Just a minus sign change in the middle. Again, I hope by the end of the term your calculations skill is enhanced significantly. You should be also precise, not only fast. Fast and precise together. Yeah, what was the question? I might be able to.
You said do both of them to calculate the top and bottom.
Calculate this value. You see all of this?
Yeah.
Calculate all of these with just the plus. You see this is the same, but with plus. That's the second value.
Keep the value the same, but just change the sign in the middle?
Yes.
Okay.
One is for the top, the other one is for bottom. If you have it, bring it. First of all, you have to be able to do not Okay, if I see just the n numbers, you can show me the numbers. Oh, is that maybe 2? I see. That's actually everything. I sent you everything. No worries. Group, please. Yeah. These are all this is 0.8. Oh, you're missing the C value. Oh, guys, I'm sorry. I think we forgot to put the C value there. Nobody mentioned. Yeah, please you get back and then let's put this value. All right. Yeah, let's put the C value there. All right. Who was Gabe responded? AJ. C top. Look at the z-axis. Look at the top on the cross section. What's the C value for the top? If you zoom in on the cross section.
6.2.
6 point. Oh, just look at the cross section. See, it's just cross section.
Oh. Apologies. Yeah. Okay. Yeah, 0.6.
0.6. So this is C top. And C bottom would be the same. So that means the two terms are again the same. So just multiply this number that we left. So 0.6 times 10 to negative 2. AJ, point before I forget. I'm sorry about that, but please recalculate and come back to me. So all of this is really our M value. Yes. If you have more value, please come to me. Let's go to see. And in giga, what do we need to get giga? If you show me the early calculation, I'm doing but that's off. Read that. See? Just because the test is supposed to be your calculator, a sick test,
I know,
you break that so you get used to it.
I have, my girlfriend borrowed it for math class, so today I didn't have it.
Yeah, yeah. Are you sure? This is plus minus, right? I want to confirm the sign. Okay, just confirm it and get back.
In what unit? No, I do not have two. Yeah, I'm actually so bad, I have a negative GPA.
Yeah, guys, if you're done, you're welcome to leave. But be prepared, be on the lookout for the test one redo on Blackboard, do on Sunday at midnight. I'll post it sometime today or tomorrow. Regular edition.
Oh, you were a beanie the other day. Yeah, you were in a lab? You were in a hat. Yeah.
Santa, why did they have?
I just got to I just signed for it I think Ed's like on and off parental leave right now because he was in for 2 days and he's out of office. Right?